Hi students, here we're going to be looking at some weirder limits than we'd had before. We're dealing with limits that give you an indeterminate form but aren't obviously factorable. And then we're going to kind of switch gears a little bit and take a look at finding limits of combined or composite functions. So if you're adding, subtracting, multiplying, or dividing two functions together, and how we deal with that, and we're also going to have some weird things going on as far as doing limits from graphs. Once again, on your version, you'll have some assignments that are recommended here to check your understanding, but without any further ado, let's go. Alright, so we're going to immediately jump into something that's a lot grosser than anything that we've looked at before, at least in terms of appearances. We don't like fractions over fractions. And one of the things that we see here is that we have two different limit problems that have the same issue. In the first case, if I plug my limit in, you might very quickly see that we get 0 on top. Square root of 0 is 0. Square root of 1/4 is a half, and a half minus half is also 0. Cool. So we've got our indeterminate form. That tells us that the limit might exist, but if I look at this, this is not obviously factorable. There are two different ways that we can deal with this. The most direct is by working with conjugates. So what I'm talking about there, you guys dealt with this in terms of imaginary numbers written as quotients. You also may have looked at this as far as rationalizing denominators that have radicals in them. The way that we're going to attack this problem, I'm going to see if it'll let me move this out of the way. Nope, of course not. I'm just going to erase that then. So the way that we're going to attack this problem is that we are going to multiply the top and the bottom by the conjugate of this weird radically expression. So a conjugate is going to be square root of x plus a half. And on top, I'm going to do the same thing, because if we don't, then we're not keeping this to be the same value. So we're still doing this limit, but now we're going to manipulate some stuff first. On top, I'm going to leave this alone, because if I can avoid actually doing that multiplication out, that's probably going to make my life a lot easier. So I'm going to write this as x minus a fourth and square root of x plus a half. On the bottom, I'm going to multiply these things out. Square root of x times square root of x gives me x. Square root of x times a half gives me plus a half square root x. Negative a half times square root of x minus a half square root x. Hey, those things look like they're going to cancel out. It's like we planned it that way or something. And then minus a half times plus a half is going to give me minus 1/4. When I look at this, those pieces do indeed cancel out. And we're left with x minus a fourth in the bottom, which you might notice we also see up top. Those can cancel out, leaving you with the limit as x approaches a fourth of the square root of x plus a half, which ends up being a half plus a half, which is 1. Okay, so just kind of a reminder what we did here. We saw that this was 0 over 0. It's an indeterminate form, so we might be able to find a limit there. We couldn't factor, so we tried to make this maybe a little bit nicer by doing something weird, multiplying by the conjugate of that radical expression in that denominator. When that happened, because this is a very specific problem type, things started to fall away. Those multiplied together gave us that same term was on the top, which let us cancel some stuff out. Okay, moving on to the bottom problem here. Here we've got the limit as w approaches 0 of w over 1 plus w minus 1. Woof! That's a mouthful and a half. Just again, to confirm for ourselves, since we're talking about things that end up with an indeterminate form, we want to make sure this one does too. 1 plus 0 is 0. I can't talk today. 1 plus 0 is definitely 1. 1 divided by 1 gives me 1 minus 1 is going to be 0 over 0. This is, again, an indeterminate form. I'm using the equal sign here to represent that this is the calculation that you get. This is not actually equal to this. Indeterminate forms are not something that you can actually be equal to. Okay. So now we're going to try to make the fraction here a little bit more pleasant to deal with and see if that helps things. And you might recall from working with rational functions in Algebra 2 in particular, that with complex fractions, you can multiply by denominators to try to make them a little bit better. Another way to think about that would be to try to combine these two pieces in the bottom and see what we get, because the top is already pretty nice. So I'm going to extend this, and we got the limit as w approaches 0. Okay. I know to combine things, I need to find a common denominator. So that's going to be 1 over 1 plus w, and then minus 1 plus w over 1 plus w. Cool. Now I can combine those. On the bottom, that's going to give me 1 minus 1 is 0. So we're left with just a negative w. And then 1 plus w on the bottom. Cool. This is still under that w, and I'm going to rewrite that as a horizontal division problem because that looks kind of gross. There's my w from the numerator, divided by w over 1 plus w. Those are going to end up canceling out when we flip and multiply, which leaves me with 1 plus w. Okay, I've done some really terrible notation here, which is that I've mixed arrows and equals, and I've stopped writing my limit as I did the work. So I'm going to ignore all that just for a second and rewrite this as the limit as w approaches 0 of, I didn't mean to cross that part out, 1 plus w, which when we plug that in, we get 1 as an answer there as well. Another weird type of limit that we're going to look at are limits of piecewise functions, and specifically having to work with one side or the other. So if we take a look at the limit we're being asked to find, which is the limit as x approaches negative 2 from the right, the problem is, as x approaches negative 2, we have two different parts of this graph. Just to kind of quickly sketch what's going on here, we don't actually have to sketch these out all the time. I just want a visual to go with this. So x plus 1 is going to be something like this when x is less than negative 2, and negative x minus 3, so it's going to go something like this. And A, we can see that the limit doesn't exist because these points don't actually, or these lines don't actually hit each other. But what's more interesting to us here is identifying which one of these is from the right side. Visually, we can see it's the guy literally on the right side here, but sometimes that's a little bit hard for us to see in terms of the notation that we use for piecewise functions. If I take a look here, I know that x is greater than occurs on the right side. So even though we don't see the visual there, we know we're using this function to make sense of what's happening here. When I plug that in, so we're plugging in negative 2, so the negative 2 minus 3. We end up getting positive 2 minus 3 is going to be negative 1. And my favorite part about this whole thing is that my graph was so far off that I believe these are going to actually meet and have the limit exist. But that wasn't important to the beginning, so don't worry about it. I'm sure that you'll find lots and lots of me making mistakes throughout all of these videos. And that's just another one. So, long story short, the answer to this is negative 1. There are lots of examples of these, of the weird limit type problems to practice your algebra. A lot of times my calculus students talk to me about calculus is the class where they really actually learn the algebra that they thought they understood before. And this is a really good example of some of the algebra challenges that we're going to have throughout this year. As promised, we're also going to take a look at some combining functions things. These things are happening in kind of a weird place. We're going to see these again a little bit later in our curriculum and then towards the end of the year. What I'd like for us to do first is just have a way to approach these things, because they're going to be showing up on your homework. So the first thing I might think about, okay, the limit is x approaches negative 2, g of x plus h of x. I don't really understand what to do here, because I've got two different graphs. I've got all kinds of things, and both of them appear to have discontinuities at negative 2. So that makes it even harder to process. What we're going to have to do is to take a look at these things from the left and from the right separately, because the one thing that we know is that if the limit is the same from the left and the limit is the same from the right, that means that limit exists at that value. So on the left side, g of 2 is approaching, g of negative 2 is approaching 1. So we've got 1, and then we're adding these two functions together. And then on the left side, we've got h, and we're approaching 4. All right. That equals 5 altogether if you're keeping track at home. On the right side, okay, for the g of x part, we've got 4. And for the h of x part, we're approaching a height of 1. And that also equals 5. What that means, since both of these limits equal 5, from the right and from the left, which we found separately, that together, their limit would be 5. Even though each function separately is not continuous, we have this gap there that's hard to see that a limit could work there. When we combine them, we can see that together they add up to 5. And just a heads up, I meant to do a composition problem after this, but the problem that I grabbed had some issues with it, so I'm going to have to make a separate video for that.